So we are going to sort of stop talking about operating system security today, and we are going to go back to CS252 and CS354 material and dive into assembly language and stacks. And the reason we care about this is that a huge number of the attacks that we see happening on the internet are because of assembly language and stacks and C. And so refreshing your mind on how this works is important, particularly homework 1. You are going to be exploiting C and x86, so you should sort of know how it works. So I will start off with sort of an overview of address spaces, of instructions, of x86 instructions. We're going to stick with 32-bit just because the numbers are shorter. It's basically the same. You replace an E with an R in the register names. Everything else is about the same. And we'll sort of look at sort of some various instructions. So after we sort of review this, I will then do a live demo, which will also be recorded, of actually compiling some code, disassembling it, looking at the assembly, stepping through the assembly, so you can see how to use these tools when you start working on the homework assignment. So let's get started. Okay, so as a quick recap, last week was all about OS security and permissions, about access control lists, about setuid, how to use setuid to sort of, setuid is really good for this notion of delegation. And delegation was you have access to something, you want to give somebody else limited access to that, so you delegate some rights to them, and typically what you do is you delegate to some program, and you trust that program will only give the person the rights you want. So if it's a setuid program, you make sure the program only does what you want. If it's a process in Windows, you make sure that process only does what you want. So that means that we have this notion of when a process is running, there's really two identities it can have. It can have the identity of the user who invoked the program, in this case the RUID Swift, or it can have the effective UID, which is root. And you can switch back and forth depending on who this program wants to be. So one of the things to remember here is that how do we make sure this model is actually secure, right? We have a program which is supposed to sort of enforce the rules that we want around this file. So the password file, we want to make sure that, for example, you can't just dump out the contents of the shadow password file. We want to make sure that you can only modify your entry in the password file. When you change your password, you can't modify anybody else's. So we are trusting the code in the password program that you use to change your password to do this correctly. So one thing we talked about on the first day was the notion of an attack surface, which is what is sort of, did we talk about it? I mean, we didn't. But there's a notion of an attack surface, which is what are the interfaces to code that is vulnerable? So if we think about a password program, what are the things you could do potentially as an attacker to try to subvert the controls it has on what it's allowed to do? Because if you can subvert that control, for example, and get it to launch a shell instead of changing the password file, you can have it launch a shell as root, and you can do anything root can do, which is, see everybody's password and change everybody's password, or hash password anyway. So this means that we need to think about what do processes do to make sure they maintain control and always do the right thing. So for password, what is the input you get to control as a user? You get to control the environment variables that are provided when this program runs. You get to control the directory that it runs in. So your current working directory is something you can control. And you get to control the command line parameters to this program. And so the challenge as an attacker is to figure out, can you use these inputs to make the program do the wrong thing? And that's what we'll be talking about on Thursday, is how you can sort of corrupt inputs and make, that is what homework 1 is subverting programs by passing them bad inputs. But for this reason, we need to know, how do those inputs get passed to programs? Where do they get stored in memory? What can go wrong when you do this? Any questions? Okay, so today we're going to talk about enough x86 assembly code so that you can hopefully read it and have some sense of what it does. It's not going to be easy. And next time we'll talk about attacks. Yes?
For the purposes of lecture and the assignment, are we assuming that memory is going to be randomly allocated versus in Or like, is there going to be for this?
We are going to be, the assignment says this, we're going to turn off most of the protections that stop, you know, there's the kind of bugs we'll be looking at have bugs that have since been defended against in most operating systems, and so we will be disabling those features so you can still use these bugs. There are ways around many of these features in some cases, like address space layout randomization and stack canaries that we'll get to. But they're sort of much harder to implement in a class setting. And so I don't want you to like spend a year doing the homework. I'd rather something fairly doable. Actually, one quick question before I go on. There was some question about the review questions that I posted. I hope those are useful. My goal for those is to sort of help you figure out what is it you should be getting from here. What are the kinds of things I want you to get to take away? Because I know in a class like this, there's a fire hose of material coming at you. I speak pretty quickly. The slides don't have all the detail. Some of the detail comes out of my mouth. And so those review questions, the hope is that you can look at them and figure out, did I understand the lecture? Did I not understand the lecture? And that is the kind of question that I would put on an exam when we have an exam. And so that hopefully is a guide for what kinds of things you're understanding. So they're not graded, they're for you to work on. As I posted on Piazza, I would prefer if somebody didn't post the answers to all the questions online. And the reason is that it sort of makes it too easy for someone else to not do the work of figuring it out and figure out if they know the answers. Because just having the answers to these questions doesn't necessarily give you everything. This is not a complete set of questions. This is a subset of all the things you should know to help you make sure you're sort of learning the right way. And you sort of miss out on that if you just have a list of questions and answers. Yes?
You release the answers to release no questions. You don't think we know the answer?
I don't have the answers written down anywhere. So there's no answers to release. You're welcome to talk to each other to figure it out. You're welcome to come to office hours, to send an email, to look up the answer online, to look at the readings. So I'm going to tell the computer. The question was, am I going to release the answers? Okay. So first question is, why, having done assembly back in 252 and 354, you thought you were done with it for the rest of your life? Why do we need to go back and look at this? So one reason is that compilers do lots of interesting things at this point. You may write some code, and the compiler may do something totally different. So for example, there's some research done here by Professor Carl Metz, and he found that you might have some code that looks like this. Memset password to 0 for some length. The idea is if you have a password in memory, you might want to zero out that memory so the password isn't just sitting around. Because somebody else who allocates memory in the future might see that password when they call malloc and figure out what the password is. So an example, Windows 95 kept your login password in memory that was globally shared to all processes in clear text at all times. You could call that, it was called a gaping security wound by the Vice President for Windows. So that's the kind of thing you want to avoid, and this is sort of clever programming or careful programming to make sure as soon as you're done with the password, you empty it out. Now the problem is the compiler says, well, frees memory, meaning that the contents of whatever was in memory doesn't matter after you call free. This means that doing the memset, nobody's ever going to read that value from the memset, so I can just take the memset out altogether, and I can just take that value, pass it to the free routine, and make your program run faster. So there's a challenge that compilers may not know when you put things into your code with an adversary in mind. The compiler may say, well, this is dead code, that'll never happen, I'll just remove it. So that's one reason to look at assembly. The other reason is that there's a lot of, in C, there's a lot of things you can do wrong that will just execute and totally corrupt memory without failing. And so to understand how and why that happens, we need to look at assembly. And to make the attacks, we need to look at assembly. So, what this means is that we sort of write code, if you're a C programmer, in this relatively nice form with integers and return values and functions. The compiler produces this assembly over here, and when people are exploiting code, it's typically the assembly they look at. They sort of look at the registers, EBP, ESP, they figure out, is there some way I can exploit these register values, I can change where they point to make it do my own thing. So hopefully you're well motivated to dive in here. So we're going to work on x86. In the past, you might have worked on some other architectures. There's actually a debate right now as to what architecture we should be using in the department. Should we use MIPS or x86 or ARM, not x86, or RISC-V or ARM. We're doing x86 because there's lots and lots of exploit code for x86, so that makes it easier. It's very popular. Almost everybody's laptop runs x86. 99% of servers in the world run x86, so it's a good target. The thing to note about this is that it has a very complicated instruction set. So one of the things this means, if you take any random sequence of bytes, there's a good chance that you can execute some of those bytes in there. They're valid instruction encodings. It also means if you have 6 instructions in a row that do something, you might be able to jump in like 1 byte offset instead of the beginning of the first instruction, but in the middle of the first instruction, and you can still execute it and do something different. And so it means that if we go back to what you see is not what you execute, the fact that you have a set of assembly instructions, you might even execute a different set of instructions than your compiler produced, because you might look at the bytes in memory and execute them a different way. So the things to note of interest here are that there's only 8 registers. And this is sort of good because it means most things are in memory. When things are in memory, they're easier to corrupt because if we can write to arbitrary places in memory, we can overwrite arbitrary values. When things are in registers, it's harder to write to an arbitrary register. Another thing to note, as I was mentioning, is that instructions are variable length. Some of them are 1 byte, some of them might be 6 or 7 or 8 bytes. So they're not nicely aligned on 4-byte boundaries. As I said, any byte boundary can be a different instruction and likely is some kind of valid instruction. The other thing is that this instruction set has lots of backward compatibilities. So the architecture was sort of initially defined in the late 70s, and you can still run some of that old code on modern processors. So this means there's a lot of cruft built into the processor to sort of maintain compatibility with these old processors. That means that you can sort of exploit this code that nobody pays attention to. So here is sort of the little history of x86 for architecture nerds like me. So originally Intel created the 4004, and then the 8008, and then finally the 8086, which was what IBM picked to build the first IBM PC. This was a 16-bit architecture, meaning that your registers were 16-bit wide, and you could have a 16-bit address, which allowed you to reference 64 kilobytes in a pointer. They used segments to expand this, so you could have 4 different segments that let you get up to about 1 megabyte of total addressable physical memory. In 1982, there was the 8186, which probably no one's heard of because it wasn't used. But then there was the 8286 that took you up to 24 bits of memory. And then finally, in 1985, there was the first 32-bit Intel processor with flat virtual memory, with page tables, and all the things that we look at. And the 386 architecture is most of what we use today, and it's most of what exploits are targeting is this architecture from 1985. Intel 486 came later, basically new microarchitecture, faster execution. Finally, the Pentium came out in 1993. You may notice the change in numbering, and the reason is that you can't trademark numbers, and Intel didn't like AMD numbering things the same way. So they switched to the Pentium name, and then Pentium Pro. So this kind of glided along until AMD released the 64-bit extension. And that's sort of what almost everybody at this point is running a 64-bit version of x86. We'll be using 32 bits as a hit just because it's a bit more convenient, although everything should work in 64 bits as well. Okay, so that is history. Now to look at the architecture itself. So in the architecture, you have a number of sort of registers. These are the 8 standard registers. So EAX, EBX, ECX, and EDX are somewhat general purpose registers. They're 32 bits wide. You can reference different parts of them. So if you want just a 16-bit value, you can go with AX, which is the lower 16 bits. If you want an 8-bit value, like you're dealing with a string, you can go with AL for the lower 8 bits. If you use AH, it's sort of that middle 8 bits there. This is sort of a leftover from when it was a 16-bit architecture before it was extended with the X, when it was just H and L. We then have these 2 special registers, ESI and EDI. These you can't split apart. These are often used with string instructions because they hold the source and destination addresses when you're doing string copy instructions. There's then sort of 2 special purpose pointers that maintain the stack pointer itself. So the stack pointer sort of points to the current top of the stack, which is actually a low address. And base pointer BP points to your current stack frame, sort of where's the data for the currently executing procedure. And there's instructions that sort of so what special purpose means is that there are instructions that don't take a register as a parameter or as an argument, but they are hard-coded which registers to use. So you can temporarily put other things in these registers in some cases, but if you execute one of these instructions, the processor expects certain things to be there. Any questions? Okay, so the next basic thing to know, and this is a review of 537, is what does a standard Unix or Windows process look like? So in a process, the memory in a process is split up into different categories of things, and those categories of things are closely related. So one of the sort of at the lowest level on the left here, usually the very bottom page in memory is marked as inaccessible, can't be used. This is where the 0 address lies. And one nice thing about this is it means if you dereference the null pointer, then you're sort of guaranteed to get a segmentation fault because the address 0 is not referenced. Now, one quick question here is what happens if you as an attacker actually map something at address 0? How would that change your system? Any thoughts? Because there is an attack where people do this. But sort of think, what would it mean if 0 was actually a legal address and there was data sitting at 0? Any thoughts? Yes? Right, exactly. So if you had code that was expecting a null pointer exception, and it would fail on a null pointer exception, in this case, it will dereference memory. So think about if you call malloc, for example, to get some memory, and when there's no memory, it returns 0. If you don't actually check for 0, you just use that, normally you'd get a null pointer exception, your program would terminate. In this case, however, you dereference that memory, and you might be able to trick the program into overwriting or corrupting things. And so people have used this, for example, by writing some code to insert into the kernel to map the 0 address in the kernel, and then sort of taking advantage of null pointer dereferences in the kernel for subverting what the kernel does. Okay, so we have text. Text is your code. I have no idea why it's called text. I would have called it .code. This is the actual executable code. It has to be marked if the processor supports an executable permission in memory. It has to be marked executable. Right next to that, we have the data section. These are initialized global variables. So if you have code that says, you know, char foo bracket bracket equals quotes hello quote, or int maximum equals 200, these variables are given reserved space in the .data section. And any references to those variables in your code will refer to addresses in the .data section. The next section is .bss, or below stack section, which again is a pretty stupid name that probably came out of the 70s. And these are globally uninitialized variables. So the thing to note is your executable program on disk has to have a .data section because you need the initial values of these things. For things that are initialized with 0, you don't need to store them on disk because you know they're 0. So that's why this is different. So .bss is a reserved space for anything that you initialize to 0. So if you have, you know, a global variable that you just initialize to 0, it goes in the .bss section. The next piece is typically the heap. So this is when you call malloc or new and you get data back. This is for dynamically allocated and freed memory where you don't know how much you'll need. The thing to note is the data and the BSS and the text sections are all fixed size because you know when you load your program how big your code is, you know how big your data is, you know how many global variables you have. We then have sort of an unused region in the middle of your address space. Then at the close to the top is where your stack sits. Your stack grows downward. And then at the very top is where your environment variables go. So when you launch a program, the environment variables are copied from your parent process into a page or a couple pages of memory at the very top. This is also where the program arguments go. If you pass something on the command line, it goes in this top section. So the thing to note is the heap and the stack grow towards each other. And the heap, as I said, is for dynamically allocated things. The stack is for local variables and to keep track of parameters and what function you're into and allow you to return from a function. So these are sort of designed to sort of allow you to either have a lot of stack or a lot of heap because they sort of share the same unused space. So if you have a very large piece of data you put on your stack, the stack will grow big. If instead you malloc a lot of data, your heap will grow big, but you better not put a lot of data on your stack then. So this allows you to have both. Now, one thing to note, this is, to some extent, a design that was invented in 1974. Modern processes are a bit more complicated because, one, you have multiple threads, and each thread needs its own stack. So typically, in that area at the stack on the top, you will have a bunch of different stacks there, and they kind of grow towards each other instead of growing towards the heap, but they're all near the top. You also can have multiple heaps now, and so they're sort of in that middle unused region, and so they can't just expand indefinitely. There's sort of a limit to which they expand, then you need to allocate a new heap region. But the fundamentals are still similar. So here's sort of an example, again, a recap of things you probably have seen a while ago on how what the stack and the heap might look like. So if we have a main function, we have an activation record for the function that goes on the stack that sort of tells us where to return to when we're done, where our local variables are. We can then call a foo function, which is called from main. Foo will call malloc and allocate some memory from the heap at these low addresses. It'll then call the bar function. Bar has some local variable numbered 7, so this goes on the stack. When bar returns, bar's frame goes away. When foo returns, foo's frame goes away, things like this. So one thing to note about stacks that's kind of interesting is that you are not allowed on Windows, you're not allowed to put anything lower than the value of your stack pointer. And the reason is the operating system is allowed to arbitrarily overwrite anything beyond the top of your stack at a lower address. And it does this, for example, when doing exception handling, it has to save your register somewhere, so it might overwrite your user mode stack. So if you put something at, 10 bytes below ESP, you might find that value randomly changes without you knowing why. On Linux, there is a 128-byte, what's called a red zone, which says the operating system promises not to write anything within 128 bytes of the top of the stack, but beyond that, the operating system might write things. So a stack is not just random memory that user mode can do whatever it wants with. It's actually memory the kernel knows a lot about what it looks like, and there's very specific rules on how you're allowed to use it. Okay, so we're going to dive a little bit more into what goes into a stack frame, and this is important because when we attack programs, what we really do most of the time, or a lot of the time, is attack a stack frame and corrupt it. So in a stack frame, with high addresses to the left and low addresses, high addresses on the right and low addresses on the left, what we have, first thing is when you call a function, you might put some arguments on the stack, so they show up there. When you actually call the function, you're going to push the return address onto the stack. This is the next address following the call instruction. You're then going to store a pointer to the previous frame. Basically, all the frames make a linked list. This lets you recover the frame for when you return. And then your local variables go after this. So remember this, because we are going to sort of see this in more detail later. But these are all the things that are sort of on the stack for a single function call. If we have nested function calls, we repeat the structure multiple times for each function in that nest of functions. So one thing to note is that a bunch of this are sort of conventions. There is a document that says if you're writing code in C and you want to run on Windows and link against Windows Windows libraries, you need to follow certain rules. The rules are things like where do arguments go or parameters go to a function, and they will say, put them on the stack. They might say put them in registers. There are rules that say which are the registers that a function can clobber and overwrite while it's executing, which are the ones that must have the same value when you enter and when you leave. And these conventions basically let you link together code because they all follow the same convention. There are ways you can get rid of this. So for example, I talked about having this frame pointer, EBP, that we'll see later. And there's an optimization that says maybe we don't need that frame pointer. So the compiler will leave the frame pointer out if it doesn't need it. There's an omit frame pointer flag to GCC that gives you this optimization. So these conventions can change based on what the compiler is doing. But we're sort of going with these standard conventions for the purpose of this lecture. So what this means is that because these are conventions on what a stack looks like, there is no actual enforcement in the hardware. The hardware can put things anywhere in memory, read things from anywhere in memory, can overwrite anything on your stack whenever it wants to. There's no controls on this. It's really up to the code you're running to prevent this from happening. And that's why it's so much fun for security people. Okay, so we're now diving into real, actual x86 assembly. There's something like 700 instructions. We're not going to go through every single one. We're going to go through maybe 8 or 10 relevant ones. So the thing to know about x86 assembly is, for one, there's two conventions. There's the Linux convention or GCC convention, and then there's the Windows convention. And the way Windows expresses assembly code is, the Windows assembler is different than the Linux assembler. And our examples here will all use the Linux assembler. On the course webpage, under resources, I have like pointers to about 10 postings that are all Microsoft Windows assembly code. But they are still useful to know how the instructions work. Okay, so one thing to know is that the instruction ends with the data length. So you can see this says sub L. This means that it's operating on long data, which is 32 bits. It could be a Q, I believe, which would mean it's 64 bits. It could be W, which would mean word, or 16 bits, or B, which would be byte, or 8 bits. So the other thing to know is that the general format is source followed by destination. So here the source is 16, the destination is EBX. What this means is we're going to take the value of EBX, we're going to subtract 16, store it back in EBX. So if you've studied a RISC architecture, you know that everything takes 3 arguments, 2 inputs and an output. On x86, a lot of times you will read the output might be read and then modified and written back again. So you can also have, the other thing about x86 is that these arguments are sort of very flexible, that you can have, for example, one of your source or your destination could be memory, they could be registers, they could be immediates. And so depending on how you write it, you might be able to subtract a value from memory into a destination register, or subtract a value in a register from someplace in memory. The only general rule is that you can almost never have two memory locations as your source and destination. Only one can be memory. If you have a constant, it's preceded by a $sign. So this is $16. If there was no $sign, then it would be an address or instead. And then if we have indirection, so we're moving the contents of something, we'll put parentheses around it. So this move L paren EAX says move what EAX points to into EBX. So this is really a load instruction. We're loading from wherever EAX points into EBX. And the percent goes in front of registers, so you sort of know what's a register instead of what would just be a variable name. Because you could have a function named EBX in your code somewhere and get very confused. So far, so clear? I see at least one nod. Okay. So you might wonder, by the way, why I'm so excited about x86 assembly. And I am, to be honest. And the reason is when I worked at Microsoft, we had to debug the Windows operating system kernel, and our only debugger was an assembly debugger. We couldn't sort of say, when something crashed, we couldn't say, show us the line of code where it crashed. We could say, look at the memory for this and give us the disassembly of the function where it crashed. But then we had to basically take our source code and assemble it in our heads to sort of look compared to the output and figure out what it was, or decompile the assembly code into C code to figure out what the code was doing. So after 7 years, everybody got pretty good at reading and writing assembly code, or at least reading assembly code and converting it back and forth to C. Okay. So here's sort of example of when you do sub, if you have 2 registers and you execute them, sub EAX, EBX will overwrite EBX with a new value. Pretty simple. So our next more exciting instruction is the push instruction. So if you want to push a 32-bit value, you put L on it because that's the size, is 32 bits is along. And so if you say push EAX, here we're showing 3 registers, EAX, the frame pointer EBP, and the stack pointer ESP. What the push does is it copies the value onto the top of the stack and increment and decrements the stack by the size of the value. So when we do push EAX, you can see where the stack pointer currently points. We are then going to store the value 7 that was in EAX on the stack, and we will change the stack pointer to have a new value. So fairly simple, pretty much what you would expect. So does anybody know, is there a reason that stacks have to grow down instead of up? Like, could you write the whole C language with stacks that grow up instead of down? Is it fundamental? I see you shaking your head. You don't think so? Right. So to some extent, the reason stacks grow down, I believe, is that memory layout picture I showed you. That when you don't have a lot of memory, you want your stack and your heap to grow towards each other. And if the heap grows up, your stack grows down so they can use all that memory. And the problem we will see on Thursday is that making stacks grow down really is the source of almost all the bugs in C are by making the stack grow down. If the stack grew up instead, we would not have a lot of these problems. But I digress. Okay, so pop is the opposite of push. Again, it takes a size, pop L. Here it will copy what is currently pointed to by the stack pointer into a register and then decrement the stack pointer. Or actually increment the stack pointer in this case. Yes?
So it's possible that the value you're popping off, just looking at assembly, is not the intended size at the top of the stack?
So the question is it possible that what you pop off is not the intended size? So it is true, you might have pushed on 2 bytes and then popped off a long, because there's no type information about the stack. So one of the things the compiler has to do is the compiler has an internal picture of exactly what's on the stack at every given line of assembly code. It knows for every offset from the stack pointer or from the base pointer what program variable is stored at that location and what type it has. But it is not encoded on the stack anywhere. And so you can definitely use that, for example, by overwriting, and we'll see again, if you overwrite the stack and corrupt it, you can take things that were supposed to be pointers and addresses and overwrite them with the contents of a string, and the architecture doesn't care. Okay, so that is sort of stack manipulation. That's how you call, that's sort of what you want to do if you want to save something to the stack or retrieve it. So for control flow, this means we want to change the place where we're executing. So here we have a jump instruction. This is an unconditional control flow. We're just going to go somewhere. We don't really care. We're always going to do it in all cases. And so the jump instruction takes a relative address. It says take the location you currently are, adjust it by a positive or negative value, and start executing there. So if we have jump -20, then after we execute this, our new pointer will be starting at k -20 instead of where we were backwards. So this, for example, in a for loop, when you get to the bottom, you might jump back to the top. So that would be a great place to use a jump instruction. There's an alternative called a branch, which takes a condition code and will decide, should I take this jump or not, based on whether the value is 0 or positive or negative or something like that. But it sort of follows the same rules of where you can jump. So another more interesting, actually, yes.
For the jump, is there a check in that opcode that doesn't allow a user to jump to unauthorized parts of memory?
So the question is there anything in the jump opcode or the way the instruction is decoded or encoded that doesn't let you jump to unauthorized places in memory? And the answer is no. You can jump anywhere you want, and you will be jumping anywhere you want for the instruction, for the homework. So that is an excellent point, that you can jump to, basically when you say a jump, the processor jumps. It's sort of up to the code running to control the processor. The processor has no idea what's right or wrong. So you can, for example, if you control a jump, you can jump into the middle of some other routine and skip a bunch of it and just execute the pieces you want. You can put data in the heap and perhaps jump to that data in the heap even though wasn't supposed to be code. So you can do all of those things. Yes?
Is there a reason there's not a dollar sign
On the negative 20 about the jump. It would seem that that's
Right, it would seem that, and I don't know the answers. To be honest, these slides were created by a graduate student who has long since left. We'll see some code later, and we can when we sort of go to the live demo, we can sort of look at code and see if this is accurate or not. It might be that there's no ambiguity. So in some cases, if there is no choice of what it could be, then you may not need to sort of throw in the $sign. If you can only jump. But I'll have to check. Yeah.
the number's negatives that you jump over to your code or backwards.
Backwards. So you're taking the instruction pointer, you're adding that offset, which in case is a negative number, so you're actually subtracting an offset. And so in that case, you were jumping backwards in your code, closer to the start of your function.
Even though the stack.
So remember, this is a code pointer, not a stack pointer. So the stack grows down, everything else grows upward except for the stack. So it is confusing. The stack, in my head, the stack is very confusing because it grows down. It just sort of breaks my mind a little bit to keep track of it. But that was an excellent question. Okay, so the other important thing to know, how do you do a call instruction? So a call instruction, in a way, is very much like a jump instruction. The difference is that it will save the next address to the stack before doing the jump. So this means that because we have variable length instructions, you need to sort of decode the instruction to figure out how long it is, and then figure out where the next instruction is, save that value onto the top of the stack, change the stack pointer, and change your instruction pointer. So here, if we see a call to foo, then we will see that the stack pointer n-4 changes. We now have the address on the stack A. We're going to jump to right after the call to foo. An instruction pointer in the register there points to foo itself. So we are sort of updating lots of different things at once with this call instruction. Okay, so the opposite of a call instruction is a ret instruction. So ret will pop an address off the stack, so it'll read an address out of the stack memory, put it into the instruction pointer register, increment the stack by the size of an address, and then start executing. So here we have a ret, we have an address A on our stack. When we return, the instruction pointer is now A, and our stack pointer is now 4 above where it was before. Okay? So there's a couple special instructions that x86 has to help with making procedure call. So I mentioned, so one of the things that is going to get stored on the stack is the frame pointer from the calling function, because we want to be able to restore its stack frame when we're done executing. So the leave instruction is an instruction that restores the previous stack pointer. It assumes the stack points to where the saved frame pointer is, EBP. So it will move the current stack value into EBP and then pop EBP. And so we will see in a minute what a standard function call looks like to sort of see why this makes sense. But you will see this at the end of almost every function where it restores the previous frame pointer. Okay, so if we look at a sort of a function call here, so we have a main function. So we see some code here, it calls foo. We then see the foo function. So what we can see are first that the registers are passed, the values are going to be passed as stack values. So in main, you can see where the base pointer is going to sort of point to the frame for the main function. The stack pointer is going to point to the top of the stack. When we start executing, you need to start pushing things onto the stack. You can either use the push instruction or you can use the move instruction. It turns out that using move with a single subtract is a little faster. If you use push, you have to do multiple subtracts, and you can't do them in parallel. Here we can execute both moves at the same time because they're independent of each other. So we're going to adjust the stack pointer. You always have to adjust the stack before you write the things because it might get clobbered by the OS. Once we adjust the stack pointer, we can now start storing data on the stack. So we're going to store our two parameters here, 2 and 1. We're then going to make a call, use a call instruction to call our foo, So this will store the next address in the program, which is EIP +2 in this case. And our instruction pointer will now point at the first instruction from foo. So this first piece of code here is called the function prologue, and it sets up the frame for the function you're calling. So it'll always store the old base pointer as the first thing it does. This is what the leave instruction expects because it's going to pop off the frame pointer. It will then move the current stack pointer into the base pointer register. So we're taking the current top of the stack and making it be the address of our new frame. So what this means is if we want to access the arguments to a function, where are the arguments stored? They're going to be at positive offsets from the frame pointer. Because you can see our frame pointer, let me move on one more. So the things we passed, 1 and 2, are going to be at offsets 8 and 12 from our frame pointer because they're in higher addresses or lower down the stack. So whenever you see something that is a positive offset from a frame pointer, that is going to be a parameter to the function you're executing. We are then going to adjust the stack. So the reason you do this is when you want to make space for local variables. This is how you do an allocation on a stack. You adjust the stack pointer to move it up, more negative, to be lower down. So we're subtracting 16 from the stack pointer, so we have space for local variables. We are then going to store a local variable. So local variables are always at a negative offset from the frame because they're between the frame and the current stack pointer, and the stack pointer is always below the frame pointer or at the same place as the frame pointer. So this is a local variable 3. Next, we are going to take our parameter, which is we know this is a parameter because it's a positive offset, and put it into EAX. We're then going to add the number 9 to EAX, and then we're going to call leave to restore the frame pointer. So you will see that our EBP gets reset, or ESP gets reset, and then EBP gets reset as part of leave. One thing to note is the convention is that the EAX register always holds the return value. So that says that this is returning EAX minus EAX plus 9. So when we do the return instruction, this will restore the instruction pointer, and we're back inside the calling code, and then we're going to adjust the stack pointer again here. So to be back where it was before. So this again is a convention. There are many, many different ways of doing this. For example, Microsoft for a while, instead of having the calling function adjust the stack here, it would have the return function adjust the stack. And the return call can take a parameter to say, as you return, move the stack pointer back some number of bytes. Any thoughts as to why you might put that in the function you're calling instead of in the function that is doing the calling? Like, why put this in foo instead of main to adjust the stack pointer? So the reason is that, one, it took a whole extra instruction in the main call here that made the main code bigger, whereas you can just make it an argument to ret, and ret doesn't really get much bigger, or doesn't get as much bigger. The second reason is suppose foo is called by 1,000 places, so now you have one instruction to adjust the stack for 1,000 different call sites, instead of having to have 1,000 copies of that add instruction. So it makes your code slightly more dense depending on how you encode function calls. So there's a lot of different conventions and how things work. This is the standard 32-bit Linux convention. Okay, so can anybody tell me what foo does? Can anybody sort of decompile this code into C code and figure it out? Okay, I'll leave that as an exercise for homework. Any questions on this before we go on? Yes?
Did it skip instruction in main?
Did it skip instruction in main?
Yeah.
What do you mean?
So let's see, moves EAX to 1 frame.
So what this is doing is main is calling foo with 2 parameters. It's calling it with the parameter 1. It's calling foo of 1, comma 2. Those are the 2 parameters. Inside, I'll just tell you what it does. Inside foo, we are going to look at the second parameter, which in this case is 2. We are then going to add 9 to it, which will create 11, and then it will return 11. And so all this function does is add 9 to the second parameter and ignores the first parameter. Yes? What?
Second parameter is 1 and 2. Oh, you just said it wrong. Got it. I understand.
Okay.
The second parameter is backwards.
Yeah, sorry about that. Okay. So, yes?
What is the 4 here?
3 comma minus 4. This is storing 3 in a local variable. It is storing so that it's just storing a local variable 3. It doesn't. The 3 never gets used. It's just for purely demonstrative purposes that the 3 is there. So you can see what local variables look like. You know, we could have had a complex function with like 100 lines of assembly, but I don't think you wanted that. Okay. Yes. I could. So the question is, can I repeat how Windows and Linux are different? And I'm not going to. And the reason is that this is a 32-bit code that neither Linux people use on Linux nor Windows. People don't really use this convention anymore in either one. And so I think spending time on the difference would not be a great use of class time. But if you send me mail, I can certainly give you pointers on how to look up the difference. In Windows, there's actually 4 or 5 different conventions you can use. And you can, on your C functions, you can say which calling convention you want. cdecl, fast call, standard call. So you can choose a bunch of different conventions in the single program unit. Okay, so high-level points. What do you take away from this other than assembly code is a hassle? One, locals are organized into, we have this bunch of stack frames. We have locals in our stack frames. Callees are at lower addresses than callers. So this means that when you write to things, if you keep writing to a local variable and you don't stop, you will tend to overwrite the data that belongs to your caller because it is at a higher address than you are. On a call, you're going to save the next instruction pointer location so you can return to it. So we're going to save an address on our stack that we're going to jump to later. And we're going to save our frame pointer EBP so we can restore our frame pointer when we return. Because we need EBP to find our local variables, we need it to find our parameters. So the contents of this frame pointer EBP is really important to executing code. And again, this is convention, and you know, if you write your own language, you can do things any way you want. So we're almost done with sort of a survey x86. So one thing to know is that x86 is little endian. Which means that if we have a 32-bit value, like dead beef, we need to know how is this 32-bit value encoded as a sequence of bytes. So what it means is that we are going to sort of switch things around. So the things that are, we're actually going to take sort of the least significant 2 bits and push them and put them first. So in this case, if we're writing out dead beef, we write out EF. From the EF and B, then the BE and D, then the AE and dead, then the DE and dead. And so this is important when you're looking at a stack to sort of know how you interpret it. It means that if you look at the individual bytes, you will see one value. If you look at it as a 32-bit value, you'll see something fairly different because you'll sort of swap the order of everything. So this is important when you start playing with things in a debugger and looking at memory and debugger, which we'll be doing shortly. Okay, so we sort of talked about simple things. What about arrays? How are arrays stored? So if you have a simple array, like a character array here, an array of bytes, what we're going to see in our assembly code, it looks similar. We've got our frame stuff at the top, push EBP, move ESP, comma EBP, sub L, 5, comma ESP. Again, that sub L says we want to reserve 5 bytes for a local variable. And what we then see down below is we see this LEAL instruction. LEAL means load effective address long. It says do an address calculation. So just like you're going to load something from an address, calculate the address, but then instead of actually loading from it, just store the address you calculated. So it basically said we've got this fancy engine in the processor to calculate addresses, and we can use it for doing math in a convenient way. So that LEAL5 EDP is going to load the address of the name pointer. It's going to load the address in the AX. We're then going to put that address of name into ESP, and then we're going to call stir copy. So what this means is that in memory, we just have a sequence of 5 bytes right on our stack frame here for this handy name array. So it would be a shame, for example, suppose you put in a string that had 6 letters instead of 5. You can sort of imagine what might happen, because if we write off the end of these 5 bytes, we're going to overwrite the caller's EBP, which means we're going to corrupt the caller's stack frame, and interesting things will ensue. So here is sort of what it looks like encoded in memory. Okay, so that is sort of an overview, and the next time we will look at how to exploit buffer overflows. So what I'm going to do now